Assalamu alaikum. Today I am going to start the lectures of category theory. So first of all, I am going to explain the definition of category. What is category? So, so what is category? Category is a framework, or we can say category is a structure which we have some data. So what is the data and category? So first of all, we are denoted category with C. Okay, so a class of objects. So first thing is a collection or a class of objects. So first thing in category theory, category is a data in data is class of objects denoted by of C. Second thing, which is a set of morphisms. So what is morphisms? A set of morphisms denoted by more of C or home of C. So what is morphism here? A morphism is a function, or we can say arrow from a object X to Y, where X is X and Y, where X and Y are the objects of category. Okay, and here object X is the domain of F, and we can say the object Y is a codomain of F. Okay, X is a domain of F, and Y is a codomain of F, where X comma Y belongs to the objects of C. Okay, so there is a morphism. What type of morphism? There is a domain and codomain, and domain and codomain are the objects of category. So, and we can say F belongs to the home of X comma Y. Means what is the home? What is the definition here? What is the explanation of home of X comma Y? But this means that all the morphisms or arrows, all the morphisms or arrows from X to Y. Home collection means the set of all the morphisms or arrows from X to Y. Means there is there are arrows, there are many morphisms from X to Y belongs to this set. This is the set. This is a collection of morphisms from X to Y. Okay. So third thing is composable pair. If F is a morphism from X to Y, means the domain of F is equal to X, and codom of F is equal to Y. And another morphism, G, Y to Z, whose domain is equal to Y, and codom of G is equal to Z. So we can compose G of F is a morphism from X to Y only exist whenever the codom of F is equal to the dom of G. So there is a morphism G of F from X to Z, whose domain is equal to the dom of F and whose codomain is equal to the codom of G. Okay. So if there exists morphism, this type of morphisms, if X to Y and G is a morphism, any morphism from Y to Z, we can compose this morphism and whose from X to Z, whose domain is equal to the composition morphism, composite morphism domain is equal to the domain of F, and composite morphism codomain is equal to the codom of G, and the main property is the dom of F, the dom of G should be equal to the codom of F. Okay, so this is the data. Now we are going to explain axioms in category. So first axioms is identity. Oh, one other, sorry, there is one more thing in data. So for all X belongs to the objects of X, object of category, for all objects, for all of X belongs to the objects of category, there exists an identity morphism ID on X from X to X for all objects. Okay, now we are going to axioms. What is the axioms? First of all, for any morphism F from X to Y, and this law hold ID on X compose F equal to F, or F compose ID on Y, F compose ID on Y. Okay, ID on X compose F, or F compose ID on Y, which is equal to F, means X, a morphism ID on X from X to X. F is a morphism from X to Y. And ID on Y from Y to Y. So if we compose this, means ID on X first, then compose with F, or if we compose this pair of morphism, ID on, first of all F, then ID on Y, both are equal to F. Okay, this identity law hold. This is the first axiom of category. So next, so next is composite composition of morphism. Composition of morphism. Next axiom is the composition of morphism hold the associative law. Hold associative law. So how can we write this axiom? For any morphism from X to Y, F, and any morphism Y to Z, which is G, and there exists a morphism Z to W, which is H. So if we compose G of F, and then this is H, so we can write H compose G of F. And if we compose from another way, if we compose G compose H, so we can write H compose G, then F. So both are equal for all condition. For all this type of morphisms, associative law hold. So this is the category. This is the definition of category. We write first. So first of all, the data review, some review about category definition of category. We denoted categories with the C. In general, a collection, a data in data, a collection of objects X, Y, Z belongs to the objects of C. A class of morphisms, a set of morphisms denoted by more of C or home of C, where what type of morphism or what type of arrow? F is a morphism. Let's say F is a morphism from X to Y, where X and Y are the objects of category, and F belongs to the home of X comma Y. What is the definition of home of X comma Y? Home of X comma Y means all the morphisms from X to Y belongs to this set. This is the set of morphism from X to Y. Okay. So next, next, uh, composition, a composable pair. If F is a morphism from X to Y and whose domain is equal to X and codomain is equal to Y, and there is a morphism G from Y to Z, so whose domain is F, Y, and codomain is Z. So we can compose both morphisms and get the composable morphism G of F from X to Z, whose domain is equal to the domain of F and codomain is equal to domain of codomain of G. Okay. So next is for all objects belongs to the object of category, there exists an identity morphism. So now next is axioms. What is axioms? Two types of axioms. First axiom is for any morphism X to Y. So if we compose F with ID on X, or if we compose F with ID on Y, so we will get F for all morphisms belongs to the F. Okay, this condition hold for all morphisms from the morphisms belongs to the more of C. Now next condition, next axiom is composition law. Associative law holds for composition morphisms, composition of morphisms. Let's say F is a morphism from X to Y and G is a morphism from Z to G is a morphism from Y to Z and H is a morphism from Z to W. If we compose G of F, then H. Okay. If we go from left another side, if we compose H of G, then F. So both are equal. Okay, this is the law. This is associative law. Hold on, composable pair of morphisms. Okay.